No? Is everybody okay on proofs? All right, so what I want to try to do today is get through logic and sets, since they all tie together, and that was where we had test one. Okay? So I'm going to use the quizzes as a guide for going through there, because if you can do the quizzes, I'm 95% sure you can do the final. I don't think there's anything on the final that wasn't on the quiz in some form or another. Okay, maybe a different question, but it's if you can do the quizzes, you ought to be able to do the final. All right? Okay. So this is, well, I hope you all will be able to see that. This is the first quiz on propositional logic. So let's start with that one. So who can tell me, first of all, what is a proposition? Remember what the definition of proposition is? I know that's on. A proposition is a statement that can be identified as either true or false. But that's an exclusive ordinance, not both, right? Both would be maybe, wouldn't it? Okay. So it's a statement that is either true or false. Okay. So, is the following a proposition? It always rains on Tuesdays.
Yeah.
It is, isn't it? Is it true? No, it's false, isn't it? But that's okay. Remember that the proposition is one that's either true or false. But definitely you can identify it. How about Tuesday is the day I do my homework? Okay, yeah. True or false, right? How about do your homework on Tuesday? No, that's an order, isn't it? But you can't say it's true or false. It's just an order, a demand. Good. It looks like you all have a pretty good handle on this. Okay. If the moon is made of green cheese, then I will do my homework. Is that a proposition? Yes. Yes, it is. Because it can be identified as true or false. Now, as we got into learning about logic, the if statement has two propositions within it, doesn't it? But it becomes a proposition of its own also. So I want to make that clear. Okay. There are two propositions here. The moon is made of green cheese and I will do my homework. Are two propositions within it, aren't they? Okay. But it is a proposition on its own.
What if one's a proposition and one's a statement?
If the statement can be identified as true or false, you'll find that the whole thing can be identified as true or false. Okay? Does that make sense?
Yeah, what if it's like an order then? What if it's an order and a proposition?
Then it's probably not going to come out as a proposition. And so really what you want to do is you want to ignore that part and look at the whole thing and say, can I identify this as true or false? And remember, with if statements, we can build truth tables, can't we? Here's another sign. If you can build a truth table for it, then it's a proposition. Does that help?
Yes.
That gives you a couple of ways to look at it.
Correct.
Yeah. Because those are good questions. I can't think of an example of one that's an order and a proposition. That's the problem. But it's a good question. It probably would not look like something that overall you can identify. How about do your homework if the moon is made of green cheese? There you go. Yeah. I don't know whether that's I don't think that's a proposition. And I'm not going to give you something like that. But you need to know that for the exercise of what you're learning here, you're going to run into things like that. Okay. So use the truth table to determine which of the following is true for this proposition. P and not Q implies not P. The proposition is never true. The proposition is true if P is true and Q is false. And the proposition is always true, and I think there's probably one more there. The proposition is true when P is false. Okay. So let's take a look at this. How many basic propositions do I have there? 2, right? P and Q. So how many rows am I going to have in my truth table? 4. Because remember, it's 2 to the power of how many basics you have. Okay? So 2 to the second power is 4. And my basics are P and Q. Now I also have not P and not Q, don't I? So let's put not P, not Q. And then I have P and not Q. And then I have the implication P and not Q implies not P. All right, so starting over here, since I only have 4 rows, I want half of them to be true for this and half false. So it'd be T, T, F, F. For Q then, I want to drop down a level and do T, F, T, F. Now, not P is going to be the opposite of P. So where these are true, not P will be false. And where these are false, not P would be true. And not Q would be the opposite of this column. So it's going to be false, true, false, true. P and not Q. Now, when I have an and, what is the truth table for and? Both have to be true, right? Otherwise, it's false. So I'm looking at P and not Q. Well, I have one false here, don't I? So that's going to be false. Here I have 2 T's, so that's true. Here I have 2 F's, that's false. Here I have 1 F, so that's false. Okay. Implication now. When is implication true? Or maybe, when is it false?
It's true when the first one is false.
It's true when the first one's false, and it's true when both are true, right? Or another way of saying it is, it's easier to say when it's false, right? It's false when the first one's true and the second one's false. If you have a true statement implying something false, then you've got something like, if it's Wednesday, we have, let's say that's not true. If it's Friday, we don't have class. Whoops, if it's Friday, we do have class, right? So that's obviously false. Okay? So, I'm looking for, let's look at where this one's false, first of all, because as you said correctly, if that one's false, the statement's true, right? So this one's false here, so that's going to be a true. Here, and here. Now here, we've got a true implying a false, because there's your not P. So that is false. Okay. Now, so is that proposition, because here's the proposition they're talking about. Is it never true? No, it's true in 3 cases. Is it true if P is true and Q is false? Well, let's see. Where P is true and Q is false is right here, isn't it? Is it true here?
No.
No. The proposition's always true. Is it always true?
No.
No. So process of elimination says it better be the first one, right?
Yes.
So let's see. The proposition is true when P is false.
Yes.
Here's where P is false, and the proposition is always true there. Does everybody see how to do that? Be careful. Be sure you know how to do that. because this one may not be real clear if you try to do it in your head. Right? Is everybody okay with that? Anybody not? Okay. So let me ask you, how much time do you have to take the file? As long as you want, right? Well, maybe a week. Remember that this is like your other tests. It's a take-home test. It's not timed. So when you run into problems like this, you say, hey, it can take me 5 minutes. Don't worry about it. Settle down and just do it. Okay? And if you can't, go review something or do something, but don't just rush through it. Okay? And don't panic. And what's the theory behind all that? Why do I do that? Because when you're out in industry, in your job, time is not going to be 50 minutes or 45 minutes for a test. It's going to be a few hours, whatever it takes, right? So when you're given a project, you want to research it. If you're not comfortable with it, you want to look it up. And so I want your test to be an example of what real life's going to be for you. Okay. Use a truth table to determine which is true for this proposition. Now we can almost build it off of this one. We need not P and not Q and not P. Okay, so we've got all of those. But we've got to change this column here and this column here. I think that'll do it for us. So let's change this one to not P or not Q. And then let's change this one to not P or not Q implies not P. Okay? So let's develop this one first. Now it's an OR statement. In an OR statement, what do we know about its truth table? It's false when? Yeah, it's only false when both are false, right? Okay? So let's look for that. Where is not P and not Q false? Well, here we go. This is two falses, so that would be false. Here we have a true. Here we have a true. And here we have two truths. Okay? So there is the truth table for that. Now, when this implies this, the only time this is false is when this is true and that's false, isn't it? Okay. So here we have three T's. So here we know that it's starting with false, so that's going to be true. But where is it that this one's true and this one's false? Well, in these two cases, whoops, that's not the not P. Here is a T implying an F. So that's false. Here's T implying T, which is true, and this is true. Okay. So do we have that right now? Should be. Okay. Now, the proposition's never true. Well, that's not the right answer. The proposition's always true. That's not the right answer. The proposition is false if P is true and Q is false. Well, here's the false. Interesting. That's interesting. So that's a right answer, isn't it? Now, you always want to test the teacher. Make sure he didn't come up with two right answers. The proposition is false if P is false. Well, here's where P is false, isn't it? And the proposition is true in those cases. Does everybody see how that would work? It's a lot clearer once you build the table, isn't it? So build your tables carefully. Make sure you've got them right. Okay, now this one just looks like it needs another column. do need P, Q, and not P. So I guess I could take out the not Q column. Good. Maybe that'll help me make some room. All right. So we need Q or P. How does Q or P compare to P or Q?
Same.
They're the same, aren't they? Remember, that's what we call the commutative law. Commute, change the direction. Anybody here know electricity, how motors work? I looked at that. There's a thing on a motor called a commutator for an AC motor. And it's because it switches the polarity and keeps the motor running in one direction. Okay. Didn't think you'd learn that in this class. All right. So, now I need the P and Q or P. And then finally, I need the P and Q or P implies not P. Okay, so let's look at these. Well, Q or P. Y'all correctly told me last time that Q or P, an or statement, is only false when both are false, right? So looking at the Q or P, this is the only time when both are false. So it must be true in every other case. Now P and Q or P is true only when both are true, isn't it? In this case they're both true. In this case they're both true. But here I have a false. And here I have another false. Okay? Now P and Q or P implies not P. This is false only when this is true, implying that is a false, right? Well, let's see. Here's the two cases where it's true and not P. It is false in both cases, isn't it? Okay? So that would be a false, a false. These two now are going to be true because the first part is false. Okay. Now, the proposition's never true. The proposition is false when P is false. Here's the falses. P is true. The proposition is always true. No? So let's look at the fourth one. The proposition is false if P is true and Q is false. The proposition is false when P is true and Q is false. Well, that is true, isn't it? It doesn't matter that it's also false up there. That's not what they're talking about. Okay? Is everybody okay with that one?
Good question.
Yes.
I don't really remember. If they both false, what does it mean? Like if the preposition.
On the implication?
Yeah, implication is false.
It's true. Because when the first part's false, we don't even care what the second part is. It's kind of like a non-starter. It's true. And why is it true? Because Aristotle said it's true. And that's the hardest part about this. Aristotle came up with this logic as a math, okay? The math of logic. And he said, well, here's a problem. If the first part isn't true, what can we say about the implication? Well, we must say one or the other because it's a proposition. Therefore, it's either true or false. So he said, okay, by definition, since we don't know the truth or false of that first one, basically, we don't know if the moon is really made out of green cheese. And we don't know if it were, what would happen. Therefore, we'll just call it true. Okay, not P and Q or P implies not P. Now that one just changed one thing, didn't it? I've changed it to an or. No, it's an and. Not P and Q or P implies not P. So this just changed to a not P. but it changes the truth table. So let's see what happens here. Okay, we still have an and statement, so these both must be true for this to be true. And we're looking at not P and the keyword P. We're looking at here, here's where they're both true, if that's true. But here we have a false, here we have a false, and here we have a false. Now, we know when a false implies anything. That's a good statement, a good question there. We know when a false implies anything, the implication is true. So here we have a true, here we have a true, and here we have a true. But what about this one? Well, this is a true implying a true. Oh, well, that's true. Would you have thought that just changing that one thing would turn this into a, what's the name for this, if I remember? Vocabulary, right? I hate vocabulary.
Truth table?
What's the name for this? It's a tautology. Tautology is when they're all true. Okay, so the proposition's never true. The proposition's false when P is false. The proposition's always true. There's the answer. The proposition's always true. Let's just look at the fourth one. Proposition's false if P is true and Q is false. Well, these two, we're talking about the proposition being false. It's never false, so those can't be. Basically, this is the proposition's always false, right? So the only one that's wrong is number 3. Okay, so what is validity? Well, validity is something we all should understand. I don't remember when I mentioned it in this class, but this is a good thing to understand. If you're having a discussion with a friend and you want them to remain a friend, okay, and they come up with, you know, if this and this, or this happens and this happens, then here's the conclusion. One of the ways to effectively argue that with them is not to try to argue their assumptions, because they're their assumptions, right? We're living in a political age right now, aren't we? So don't argue their assumptions. See if when they're true, do they derive their conclusion? Well, that's a much nicer way to deal with it, because now you're saying, okay, let's assume you're right. And you hear that, right? But you know what? That's a nice thing to do. Let's assume you're right. Does this always follow? If it doesn't always follow, then you have an invalid argument. And your friend will agree with you. I hope. Okay? Sometimes it gets emotional. But hopefully they'll agree with you. So this is a good way to have a discussion with a friend and somebody you want to remain a friend, right? Or even if it's somebody that's not a friend, but you want to keep it friendly. Okay? It's a professional way. It's also the way that lawyers do it. If you go to court cases and you have lawyers questioning a witness, sometimes you'll see them say, well, let's assume that you're right. Does this follow? And sometimes the lawyer person knows ahead of time it's not going to follow. And then the jury is automatically agreeing with the lawyer. Right? And you didn't disparage the witness, because the witness might be a professional witness, like the coroner or somebody like that. All right, so if there's a tractor-trailer accident on I-75, I-75 is blocked and Highway 41 is blocked. Highway 41 is not blocked. Therefore, there's no tractor-trailer accident on I-75. Now, doesn't feel right? Well, let's see. If we put this together, we might want to say that tractor-trailer accident, we'll call that A, Then 75 is blocked. We'll just use, how about 75? And 41 is blocked. Now we also have up there an assumption that Highway 41 is not blocked. So not 41. Then we have accident implies, well, let's see, we better do the and first. We have 75 and 41. In other words, they're both blocked. And then we have accident implies 75 and 41. How many rows am I going to have? 8, right? How many basic propositions are there? There's accident, there's 75 blocked, and there's 41 blocked, right? So that's 3. 2 to the third power now is 8. So you take half of the first one and make them trues. And then half of them false. The next one, you come down a level. So this would be 2 T's and 2 F's. 2 T's and 2 F's. And then the third one, you come down to TF, 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 TF. Why do I do that? I should have every possible combination of T's and F's. Okay. Now, not 41 is the opposite of this. So that's F, T, F, T, F, T, F, T. 75 and 41, well, that's an and, so it's only true when both are true. Okay. And then accident implies, so over here implies this, that's false only when this is true and that's false, right? So here's a TF combination, so that's false. And here's another TF combination, right? So that's false. Here's a TF combination, so that's false. Okay? Now these are all falses, aren't they? So these are going to all be trues. And the top one are 2 T's, so that's true. Okay. So, what's the conclusion? There's no tractor-trailer accident on I-75. But, if we look at the two assumptions, the if statement we're going to assume is true, aren't we? And there's Highway 41 is not blocked, we're going to assume is true. So we're looking at the rows where this is true and the not 41 blocked is true. So where are those? Well, it's not here, it's not here, not here, not here, here, not here. Here's one, not here, and here's the other. See the true and the true, true and the true. So that's where those two assumptions are true. Okay? Therefore, there's no tractor-trailer accident on I-75. So looking across these rows, I want to now look at accident. And I find out there's no accident there, and there's no accident there. So what felt like an invalid argument is valid. Interesting. Okay. Now let's look at it a little closer. If I-75, if there's an accident on I-75, 75 is blocked and 41 is blocked. Remember, if there's an accident, 41 is blocked, right? So if 41 is not blocked, there's no accident. Now, when we first did this quiz, I had the same problem you're probably having. I looked at it, and I'd get it one way, and then I'd get it another way. I woke up in the middle of the night getting it one way or the other. Okay? because I want to be able to teach it the next day. These are kind of like tongue twisters. They're brain twisters. They can get you going one way or the other. Okay, well, here's one that is a little bit different than that, isn't it? Okay. If there's a tractor-trailer accident on I-75, I-75 is blocked and Highway 41 is blocked. Highway 41 is blocked, therefore there's a tractor-trailer accident on I-75. Well, these two rows that we looked at are no longer the rows we need to look at, because we want to look at where this is still the same statement, isn't it? This is the opposite. So we want to look at where this is true and this is true. Well, 41 is blocked is this column, not that, it's this column now. And I want to look at where this is true and this is true at the same time. Well, here, they're both true at the same time. Here, they're both true at the same time. Here, they're both true at the same time. Okay? Now, the conclusion is there's a tractor-trailer accident on I-75, isn't it? Well, here there is an accident, right? But I got to look at all those rows. Here there's no accident, and here there's no accident. Well, so that's an invalid argument, isn't it? Okay. And invalid because it could be one way or the other. It's not one, it's not solid. So, let's think about this for a minute. If there's an accident on I-75, 75 is blocked and 41 is blocked. 41 is blocked. Does that mean there's an accident on 75?
Could be an accident on 41.
Yeah, it could be an accident on 41. It could be construction on 40. Well, there is construction on 41 right now. Anybody trying to get from here to the Galleria, by the way? The other day it took me about 45 minutes.
Jeez.
Because they're putting in new sewers or something. Yeah.
441 doesn't mean that it is blocked or not blocked.
It is blocked.
Okay, so the one with the space line in front of it means it's not blocked.
Yeah, that's right. And that's why I did it for the last question, really. Because the last question was it was not blocked. Yeah. So this time I looked at the 41, meaning 41 is blocked. Everybody see that now? Yes, sir.
So, you saying
No,
something?
I was just going to say, so that is true.
Oh, yeah, what is the right answer?
Yeah.
Yeah. So, it's false, isn't it?
Right.
Because it was true in one case, but it's false in
All the other cases.
other cases. So it's not valid because sometimes it's one way and sometimes it's the other. Okay. Now, if it was always false, it would also be invalid, right? Okay. But in this case, thinking about it, thinking it through, yeah, 41 could be blocked because of an accident, but it could also be blocked because of other things. So therefore, it's not valid to say that if 41 is blocked, there has to be an accident. That's what they are saying in their argument.
For the previous question,
Uh-huh.
what did we look at in order to determine that it was true?
Because that one said 41 is not blocked,
Okay.
so I looked at this column instead.
Uh-huh.
And when I looked at this column, what I found out was it's false here. Let's see. No, I had to look at where they're both true, didn't I? So where they're both true was here and here. Okay? They're both true there, they're both true there.
So,
And then when you go across here, you find out there is no accident on I-75.
the one, all the one on the right, what does it mean, like the whole thing? What does it imply?
That says if there's an accident, then 75 is blocked and 41 is blocked.
Okay.
So that is really this first statement. And we assume it's true because it was given to us. And in the argument, you want to assume all the givens are true. And see then if the therefore follows. In other words, if the therefore is always true also, when those are true. Does that make sense? Did I straighten out the... Because I understand it. When you first see these things, wait a minute, there's a lot going on here. that was the first quiz on propositional logic. So is everybody okay with propositional logic and truth tables? Okay. So let's look at predicate logic. Now, one of the first things on predicate logic that I want to discuss is this idea of the key. What's up there at the top is the key. And people get confused because X is used in more than one case. It's not there anything magic about X. It could be Y or Z or Q or anything you want for a variable. It's like a variable in math, okay? So all we're saying is, if you see S of X, what that interprets as X is a student. It's really like a set, isn't it? It's like saying the set of all students is called S. And whatever I put in parentheses says that's an element of that set. Okay? On the other hand, if I have B, capital B with some element, it means that element is a book. But they just used X because it's an example, right? You're not going to use both of them in the same sentence, or else you're going to confuse people. Does the X mean student or book? All right? So for the key, it's one thing. For the sentence, it's got to be two different variables. O, big O, okay, big O. It's not the big O from your project. O, XY means X owns Y, first owns the second. And L means the first likes the second. Okay? So now, we also know that the upside down A stands for all, for each, for every. You can read it any of those ways, they all mean the same thing. The backwards capital E stands for there exists. If I said for every, does that mean there is one? No, you can use for every and none exist. Okay? However, if you say there exists, that means there does exist at least one. One or more. So it's very interesting. We think of the for all or for each as being the bigger thing. Sometimes it can be the smaller thing, because there are none. So, our job here is to interpret into symbolic language the sentence, each student likes a book that he or she owns. Well, let's go read the sentences and see if they make sense. Where X is a student implies there exists, wait a minute, are we talking about all X's or just there exists an X? We didn't set up the variable, did we? And this relates to programming. If you don't set up your variables and you start talking about them, I mean, are they strings or are they integers? What are they? Right? That's kind of the analogy. So this is an invalid statement here. Okay, now this says for all X, where X is a student, it implies there exists an X where X is, oops, did I just overwrite my variable? I redefined the variable as something else, didn't I? Will that work in programming? Not very well. Okay? I mean, it might work, but it ain't going to do what you wanted it to. So that one gets thrown out. And by the way, big hint, I think there's one of those in every question. So right away, look for those and throw them out where the variable gets to be defined. Okay. For all X, where X is a student, implies there exists a Y, where Y is a book, and the student owns the book, and the student likes the book. Oh, isn't that what we were trying to say? Okay. What's wrong with the last one? For all x, where x is a student, implies there exists a y, where y is a book and the student likes the book. Well, wait a minute. They have to own the book, don't they? So, third one is the right answer. Is everybody okay with that? Okay. Same key. If a student owns a book, he or she likes it. Okay. Now the own must come into the first part, doesn't it? Because if they own it, then is the arrow away. They like it. So let's see what that one looks like. Well, that first one up there, again, they don't define whether it's all x's or there exists an x, so that's right away wrong. The second one, for all x, where x is student, x is a book, there's that one you want to throw out every time. For all x and for all y, where x is a student and y is a book, it implies that the student owns the book and the student likes the book. I don't think that where x is a student and y is a book implies that they own the book, does it? Doesn't it say if they own a book? Well, look at this last one. For all x, for all y, where x is a student and y is a book, and the student owns the book, it implies they like the book. Isn't that what the sentence said? So look at these carefully and learn how to read them in English as you're looking at the symbols. There is a book that no student likes. Okay. Now, are we talking about all students? When you say no student, we really are talking about all students. But are we talking about all books? No. Okay. That first one up there is not going to make sense because it's x and x. Let's look at the second one. There exists a y where y is a book, and for all x where x is a student, it implies the student doesn't like the book. That looks like a good candidate, doesn't it? Okay. But let's keep going. This one doesn't have any for alls or for eaches. There exists a y where y is a book, and for all x where x is not a student, it implies that x likes the book. So all the x's that are not students like what? They're cars. They're the moon. Yeah, you don't want that one, right? Okay. What is it that the student, there's no student that likes it, right? So it's this one. X does not like it. For all students, they don't like that book. That's another way of saying no student does like the book. Now this is a little different. The last one said that it's the same book that nobody likes, right? There exists a book that nobody likes. This one is saying each student does not like at least one book. It could be a different book for each student. See that? And so it really is about where we define our variables. In the first one, for all x, where x is a student, it implies there exists a y where y is a book. And, who doesn't like what? The book doesn't like the student. Watch out for those, okay? Remember the goats that ate the wolves? Okay. So it's close though, isn't it? All right. Let's see, the second one looks like it's redefining X again. The third one, for all X, there exists a Y, where X is a student implies Y is a book, and the student doesn't like the book. But here's the problem. The for there exists is up here at the beginning of the sentence. It implies same book. What we want to do is we want to have a student identified first and then say there exists a book. And that's a little subtlety. So for all X where X is a student, that implies there exists a Y where Y is a book and the student doesn't like it. Okay, do y'all see the difference? That's a little subtle, but it is a big difference. Okay. Every student owns a book, but there is a book, but there is no book that all students own. Well, it turns out the first part of each one of these statements is the same. We look up here. So let's see if that's correct. I hope it is. For all X, where X is a student, it implies there exists a... Well, that can't be. That one's going to be wrong right away because we're using X for both of them. For all X where X is a student, there exists a Y where Y is a book, and the student owns the book. And I think that's common for the first three. It's the second part we want to look at. The first one says, and there exists a Y where Y is a book, and not for all X where X is a student, the student owns. That's a little clumsy, isn't it? How about the second one? First part's good. And there does not exist a Y where Y is a book, and for all students, all X where X is a student, the student owns the book. And there does not exist a book that all students own. Interesting. That one looks pretty good, doesn't it? And let's see if we've got any confusion in number 3. This is the same as that last one. There exists a Y where Y is not a book. What is Y?
Anything that's not a book.
It's a wrench. Yeah. So that one can't be. So sometimes you want to look for a best answer too, right? So it looked like number 2 is the best answer. There does not exist a book that all students own. That's right. There is no book that all students own. Another way of saying that is there does not exist a book that all students own. Okay. If a student likes a book, he or she owns it. Well, where does the like come? Is that in the first part or the second part of the implication?
First part.
First part, because if they like it, then they own it. So, the first one says, for all X and for all Y, where X is a student and Y is a book, and the student likes the book, it implies that the student owns the book. That is pretty good, doesn't it? The second one is X has been defined twice. The third one, they forgot to define the quantities. Down here, for all X where X is a student, and whoops, we forgot to define whether it's for each or for all, or there exists, right? So the only one that's plausible is actually the first one. Okay. So another approach to all of these is be good at identifying bad answers, okay, that are not possible. All right. Inference. Again, same predicates. Susie is a student. If a student likes a book, he or she owns it. Therefore, Susie owns a book. First of all, can you look at that and tell me if it's true or false?
False.
It's invalid. And what's wrong with it? she owns the book, does it? It doesn't say she likes
She
it.
likes,
Yeah, doesn't say she likes the book. So that one you can throw out that way. Now these are a little more subtle. If this one is true, does it follow that this one's true? Well, there exists an X where X is in P, and there exists an X where X is in Q. Is that the same as there exists an X where X is in P and X is in Q? Well, the first one picks an X and says it's in P, right? And then it picks an X and says X is in Q. Does that say it's the same X? No. The second one says pick an X and it's in both. Okay. Knowing set theory, this is an intersection, right? This is two different sets, and we don't know whether there's an intersection or not. They may be what we call disjoint. So that is false. Okay, the second one says, for all X, where X is in P, it implies there exists a Y where Y is in Q, and there's a relationship between X and Y. If that's true, does it follow that there exists an X and there exists a Y where X is in P and Y is in Q, and there's a relationship between X and Y? That's a little tougher to see, isn't it? Well, let me ask you a question. In the first one, does it say there is an X? Remember that the for all, for each, and for every can mean there is none. Okay? But the there exists says there is at least one. There exists at least one. So, no, it does not follow. Okay. This one says, for each X, or for all X, X is where X is in P, and there exists a Y where Y is in Q. So does that follow that for all X, there exists a Y where X is in P and Y is in Q? The answer to that one is yes, they're the same. If that had been an implication, it would change it. Because where you define the for each or for all can be different if you say it implies something. Then you're talking about each one. But here, it's an and statement, and they stand separate, so they are equivalent. So that's a truth. Okay, so that's the end of the predicate logic test. Yeah, we have time. Let's go over predicate logic 2. Now this is the one where G stands for goats and W stands for wolves, right? And reading that, it says for all Z's where Z's a goat, it implies there exists a wolf, or W where W is a wolf, and the wolf ate the goat. Okay? So, does that mean that every goat is eaten by a wolf? For each goat, there's a wolf that has eaten the goat. So every goat is eaten by a wolf. Yep. How about there's a wolf that has eaten every goat? No, that means it could have been one wolf that ate all the goats, right? Some goat was eaten by a wolf. That's not the best answer, is it? For every goat, there is a wolf that it has eaten. We didn't talk about goats eating wolves, did we? So the best answer, and this is what you want to look at on these, it's the best answer. Every goat is eaten by a wolf. Okay. For all Z's, so let's move this over. For all Z's, where Z's are goats, implies there exists a W, where W is a wolf and what? The goat has eaten the wolf, right? Every goat is eaten by a wolf. There is a wolf who has eaten every goat. Some goat was eaten by a wolf. Every goat has eaten a wolf. The last one, isn't it? This is just teaching us to read carefully. Okay. This one says, there exists a Z and there exists a Y, where Z is a goat and Y is a wolf, and the wolf has eaten the goat. Right? So, does this say a wolf ate a goat? Does this say there's a wolf who has eaten every goat? How about every goat was eaten by a wolf? And a goat has eaten a wolf. Let me look at something for this one. This one is rich. So which one is the best answer here? That a wolf ate a goat? That's all it says. There exists a wolf that ate a goat. That's the best answer. Now, on these, there can be more than one right answer. So check all that apply. More than one answer may apply. Okay. For all Z's and for all Y's, where Z's a goat and Y's a wolf, it implies that the wolf ate the goat, right? Or that wolves ate goats. So, when is this statement true? Is it true if there are no goats? It is, isn't it? Okay. What about if one wolf ate all the goats? Well, the implication is there are other wolves around, right? And if one wolf ate all the goats, what about the other wolves? They couldn't eat the goats, right? But we said for all Z's and for all Y's. How about one goat was eaten by all the wolves? Again, same problem, isn't it? There's more than one goat. How about there are no wolves? That's true too, isn't it? So it's the first and the last. Another way of looking at it is, you might want to say, well, if this is false, there are no goats, then the and statement is false, and a false implying anything is true. And that would apply to this and this. That's another way of looking at it. And the last one. Under what circumstances is this statement false? remember, it's an implication, so it's false only when the beginning part is true and this is false, right? So what does this say? For all z's and for all y's, where z's are goats and y's are wolves, it implies that the wolf ate the goat, or the wolves ate the goats. So, when is it false? If there's a wolf that did not eat a goat, that would make it false, wouldn't it? If there's a goat that was not eaten by a wolf, that would make it false, wouldn't it? If there are no goats, if there are no wolves, so it's the first two. Okay? Okay. So that gets us through both of the logics, right? So what else do we have to do? Look at sets. And we should have plenty of time. Okay. So looking at this, are those two sets identical? Everybody see that in the back of the room? Okay. Are those two sets identical? It's the empty set, remember that phi, Greek letter phi, or the zero with a slash through it, means empty set, right? So that's the empty set, and the second is a set containing the empty set. Are those two equivalent? Remember what cardinal number is, cardinal value? That's the number of elements in a set, right? So for the empty set, what is the cardinal value? 0. For that second one, what's the cardinal value? 1. There's something in that set. It might be the empty set, but what's the difference? Well, let's take a blank disk. You just bought a new disk. Let's use solid state disk, it's even easier, right? What's on that disk?
Nothing.
Nothing. You create a file for keeping track of customers and you define the file, but there's nothing in it. What's on the disk? The file, or maybe the index of the file, but there's something there, isn't there? But it's empty. Do you see the difference? Okay. And that's why I wanted, on all these things, we should see them in light of our profession in computing, right? There is a big difference. Okay. How about these two? The empty set and this is, we're going to learn how to read this. This is the set of all x, and the vertical line reads such that. In other words, conditions for what an x is. So it's a set of all x such that x is an odd number divisible by 2. Are those equivalent? How many elements are there in the first one? How many elements are there in the second one? How many odd numbers are divisible by 2? 0. They're equivalent, yeah. Because now I have defined what an empty set is. Are these two sets identical? The first set is the numbers 1, 3, 2, and the second one is 3, 2, 1, 1, 2. Are they equivalent? This comes from something we discussed about sets. If you list an element of the set more than once, it makes no difference. So they are identical. Yeah. Just because I listed the 2 and the 1 twice in that second one does not change the set. The order in which you list the elements of a set makes no difference either. Okay. So those two sets are equivalent. Or identical. How about these two sets? The set containing 1 and the set containing 1 and the set containing 1. And again, we can go by the cardinal number thing, can't we? The first set has a cardinal number of 1. It has one value. Not the number 1, it's one value. The second one has 2 values, doesn't it? Or 2 elements. Not 2 values, but 2 elements. Are these two sets identical? B minus A and A minus B?
No.
Good. No, they are not equivalent. And let's just take a minute and show that. And I like to use B, A and B like this because it shows you that the listing is not important, right? So let's say that this is 1, 2, 3, this is 3, 4, 5. Now, B minus A, that's the first one. Says you start with B and you take out anything that's also in A. Well, the only thing that's in both is 3, isn't it? So the 3 is also in A. So B minus A would be the set 4, 5. Everybody see that okay? Now, A minus B. Well, you start with A and you take out anything that's also in B. Well, again, it's the 3. So this is 1, 2. Very different. What about B intersect A and A intersect B? Are they identical? Yes, because what that says is we're looking for that intersection of the 2 roads, the area that's in common to both. The 3 is in common to both, isn't it? And whether I say B intersect A or A intersect B, I'm still just going to get the number 3. It is the element that's in both elements. Okay. How about B union A and A union B? Are they equivalent? They are, because what it says is united. If I unite the 2 sets into 1, it doesn't matter whether I started with the first and united it with the second, or started with the second and united it with the first. I'm still going to get all the elements that are in both, right? Would I list the 3 twice? No. No, just list it once. Doesn't make any difference, but properly you don't want to do that. Any more than if you wanted to took all the students who have classes on the Marietta campus and all the students who have classes on the Kennesaw campus, and you formed a union of the 2, would you have duplicates? You might for a while, but what would you do in your program? You'd go through and eliminate them, wouldn't you? Okay. Yeah. Okay. Are these 2 sets identical? They are, because it's the same operation, isn't it? Anybody tell me what rule that is? Do you remember the 5 rules? Commutative, associative, distributive, inverse, and identity. This is associative. You can associate the numbers of the sets in any order. Okay. Union is associative, and so is intersection. Okay. Now let's take some real examples. If I have those 2 sets, A is 1, 2, 3, B is 5, 4, 2, 3, A union B, is that 5, 3, 2, 4? And why not? Forgot the 1, didn't we? Yeah, very good. A intersect B, is that 2, 3? Everybody see that? It is, isn't it? That's the common, what's common to the 2. How about A minus B, is that 1, 3? No, because it should be one alone, shouldn't it? Because the 2 is in both. What about B minus A? Is that 4, 5?
Yes.
Yeah, that is true, isn't it? Okay. Okay, in this case, I have 1, 2, 3, and 4, 5, 6, 1. It is B minus A, 4, 5, and 6.
Yes.
Yes.
It is, isn't it? The 1 is the only thing in common. Is A minus B 2 and 3?
Yes.
No. A intersect B, is that 2 and 3?
No.
No, what is A intersect B?
1.
1, good. A union B, 5, 3, 2, 4?
No.
No. Not even close, is it? This is not number. Okay. All right. So we got through both logics and sets and quizzes. Any questions on those topics? All right, what you need to be doing, first of all, get the project done if you haven't. But be looking at these by looking up the chapters on the internet that we're covering these topics, okay? And kind of glance through those, looking for things where you still don't feel 100%. And bring those things in on Monday, or next Friday, okay? And I think we're on schedule. The final comes up, but the week before Thanksgiving, I think, is the way it's set up right now. So I'm hopefully going to get you reviewed on everything before then. And then on that week, make sure that you take the quiz once before that Friday class, or the test once. So you can actually bring questions into class, because I'm going to deal with the final the same way I've dealt with all your tests. If you have questions on them while it's still open, please bring them to class, because the goal for me, for you, is learning. I don't mind talking about a question on a test if you don't know it. That's your signal and my signal that I need to help you. Okay? So make sure you do it once before class. Yes, sir.
It looks like that opens up on the 14th to the 16th, so will that be changed so there's a class date between that?
Yeah, it looks like I do need to do that, don't I?
It opens on the 14th and closes on the 16th.
What is the 14th?
Monday, and then that class day is the 18th.
Yeah, I need to make it that following Sunday.
But it'll be open that week.
Yeah, I'll go change that. Yeah. That probably came from one of the other classes. I have a Monday, Wednesday, Friday class, and they can do things a little more accelerated. Okay. Anything else? Okay. Then that does it for today.